All right, we're going to end topic A here by going straight through a couple of examples, start to finish, where we want to write a definite integral that represents the value of an area under a curve, and then actually find that exact area by setting up that limit and the Riemann sum. So in our first example, our goal is to first write the definite integral that represents the value of the area under the graph of f of x equals x squared minus 2x between x equals 2 and x equals 4, and then we'll evaluate it with that limit and Riemann sum. So I'm going to start just by sketching this. Again, never hurts to use a calculator for that part, right? Or Desmos or whatever you're using. And looks like we've got a right side up parabola this time. Between x equals 2 and 4, x equals 2 is the x-intercept here, so I'm looking at this little section kind of over here. So the actual area that I'm finding is this. Almost looks triangular, but I know that actually that edge of that parabola is slightly curved. All right, the notation would be, we can write this as a definite integral from 2 to 4 of the function itself, x squared minus 2x, remember that represents the heights of all the little rectangles, times dx, which represents the base, like the delta x, of all the little rectangles. And in order to actually calculate this, we're going to take the limit as n goes to infinity of the sum as I goes from 1 to n of f of a plus I delta x times delta x. In this problem, it looks like my a and b are 2 and 4. Therefore, I can calculate my delta x as b minus a over n. That would be 4 minus 2 over n, or 2 over n. So, I've got the limit as n goes to infinity of my sum, and this will be f of a here is 2 plus I times delta x. So that would be 2I over n. And then multiply by delta x, 2 over n. All right, so I have to plug 2 plus 2I over n into my original function. I'll just remind us right here, f of x was x squared minus 2x. So plugging this in is going to be a little bit of a mess this time, but we'll get through it. We'd have 2 plus 2I over n squared, subtract 2 times 2 plus 2I over n. Sorry about all the 2's. And then that gets multiplied by 2 over n. All right, algebra time. Squaring this is going to give me 4, plus this product would be 4I over n. And there's going to be one from the inners and one from the outers, so another 4I over n, plus the square of that would be 4i squared over n squared. Then I've got a minus 4 and a minus 4i over n, all multiplied by 2 over n. All right, let's see if anything good happened, hopefully. Looks like we can subtract off those 4's, or they get rid of each other, I should say, and then one of the 4i over n's goes away as well. And so if I now distribute, I would have 8i over n squared and a positive 8i squared over n cubed. So it looked pretty bad for a while, but it simplified rather nicely. All right, I'm just about to the point where I can use my sum formulas, and I'm actually going to go ahead and find those on my list here. As I said, these are in your lists that you can use on tests. You'll notice that the summation formulas are right here, as is the definition of the Riemann sum. I do apologize, it's in just a very slightly different form. I put the a plus I delta x there, but that is what goes into for the c, right? So I'm getting ready to use these formulas. And for this first one, I'm going to pull out the 8 over n squared. And then it'll be the sum of the i's. And here it'll be 8 over n cubed. And then it'll be the sum of the I squareds. So I've got 8 over n squared. And then I'm just going to use my sum formula for the i's. n plus 1 over 2. Plus the 8 over n cubed, and then the sum formula for the I squareds, and that's this one right here, n plus 1, 2n plus 1 over 6. All right, I know there's a ton of writing going on here. I'm just going to say, even though I know it's a pain, keep your notation really clean. It's so easy to make a mistake if you start shortcutting the notation. All right, what have we got? 8 divided by 2 is 4, and I can get rid of one of the n's. So that first term, I'm going to get 4 times n plus 1 over just n to the first, plus 8 and 6 are both divisible by 3, or by 2 rather, so I'll get 4 and 3. And again, I can get rid of one of my n's. So I'm going to get 4, and I'm going to go ahead and multiply those together right now. 2n squared plus 3n plus 1. And then I've got 3n squared on the bottom. All right, we're getting close now. Finishing my algebra, I'd have 4n plus 4 over n plus 8n squared plus 12n plus 4 over 3n squared. And again, we've done so much here, we're going to go ahead and use the shortcuts. I definitely see that I've got the same power of n top and bottom, so I can go with the ratio of the leading coefficients, 4 over 1. And the limit here would be 8 over 3, same reasoning. So I'm going to end up with 20 over 3. or approximately, is that 6.67? For this area. All right, that was a lot of work to get that, but hopefully you can see if you kind of follow the process, there's very definite steps to go through, which tends to make even a long process a little simpler, right? You don't have a lot of decisions to make. It's just a matter of kind of trudging through the process and the algebra. Before we move away from this problem, I want to go back to the fact that when we had the calculator and we had the graph here, there's actually a way to get the calculator to tell you the area under the curve. Now, obviously, you're going to have to show all these wonderful steps to me when you do your homework and on a test, but it's a good way to check problems like this. I'm thinking on here I may not quite be seeing the y value yet when x is 4, so first thing I'm going to do is just fix my window. I'm going to go up a little bit higher. Let's go up to a y max of 10. I just want to make sure I can see that y value when x is 4. And if I now go into my calc menu, second calc, down here, option number 7 says integral. Well, this thing that we're doing was called a definite integral, right? It's now going to ask me for the limits. And in this particular problem, we were going between x equals 2 and x equals 4. So my lower limit, I'm just going to type in a 2. And my upper limit, a 4. And when I hit enter, it's going to do two things for me. It's first going to shade the area so I can see the area that we just found. And then notice right down here, it actually gives me the value. 6.6 repeating, 6.67, or exactly 20/3. So again, at least for right now, you can't use that as your only way to find these areas, but you can certainly use it to check your work. All right, let's do one more problem to wrap up this section. In this last example, we would like to first write a definite integral that represents the value of the area under the graph, f of x equals x cubed plus 3, between x equals 0 and x equals 2, and then we'll find that exact area using that limit and that Riemann sum. So I always like to sketch them first, just so I have an idea of what I'm talking about. If I graph x cubed plus 3, I can certainly see that I've got that x cubed function just shifted up 3. So it kind of looks like that. And we're going from x equals 0 to x equals 2. So we'd be looking for an area like this. All right. To write the definite integral, I'm going from 0 to 2. The function itself, whose area I'm going under, is x cubed plus 3. That's like my height of my rectangles. And then I multiply by dx, which is the base of the rectangle, so I'm still seeing base times height, area of the rectangles. And the way we evaluate this is by taking the limit as we go to an infinite number of rectangles of our Riemann sum. All right, in this problem, delta x, which is always b minus a over n, looks like my a value here would be 0, and the b value would be the 2. So we'd have 2 minus 0 over n, or just 2 over n for our delta x. And let's plug everything in over here. So I would have f of a is 0, so I'm not even going to bother writing it there. And then I have I times delta x, so that would be 2I over n. You will find very quickly on these it's really nice when a is 0. It's a much simpler function when you plug it in. I then have to multiply by delta x, which is 2 over n. Oh, getting a storm here. You can probably hear the wind howling. All right, let's keep going. We have the limit of this sum and I have to plug the 2I over n into my original function, x cubed plus 3. So I'd have 2I over n cubed plus 3. And that gets multiplied by the 2 over n. So I've got 8I cubed over n cubed plus 3 times 2 over n. And when I distribute, I'm going to get 16I cubed over n to the 4th plus 6 over n. All right, everything's all simplified, and I'm ready to bring in my sum formulas. So let's see here. Oops, let me pull some constants out. This first one would be 16 over n to the 4th times the sum of I cubed. Plus the second one, that's just a constant. There's no i's in it at all. So I'm just going to leave that as the sum of 6 over n. So I've got my 16 over n to the 4th. And then the sum of I cubed, again, that's just something that you can look up. That's this n squared, n plus 1 squared over 4. Plus 6 over n is a constant since there's no i's in it. So we just get that constant, 6 over n times n. Right? And again, I'm using this one. The sum of a constant is the constant times n. So a little more algebra here. 4 goes into 16 4 times. And I can get rid of n squared, top and bottom here. So that's going to make that an n squared. So this turns into 4 times n plus 1 squared over n squared plus 6. So almost there now. If I square that out, that's n squared plus 2n plus 1. Which gives me 4n squared plus 8n plus 4 over n squared plus the 6. And again, same power, top and bottom. So as n goes to infinity, that limit's just going to be 4 over 1, or 4, plus the 6, giving me a final answer of 10. So the area under that curve should be 10. Let's take a quick look at the calculator and verify that result. I already had my function in here, the x cubed plus 3. So if I go to the second calc, and option number 7, oops, I went back too far. Option number 7 is the integral, which gives me the area. And I was going from x equals 0 for my lower limit to x equals 2 as my upper limit. It drew it, and notice that it does indeed give me 10 for the value of the area. My picture wasn't great. It goes up a little more steeply than what I drew, but we're okay. We do indeed get an area of 10. All right, that brings us to the end of topic A.